Okay, I'm back again. Can anyone hear me? All right, thank you very much, Rose. All right, I'm seeing some new faces in the house. So if today is your first time joining our section, could you just signify by raising your virtual hand? Okay, thank you, Precious. Who else, please? Okay, Emmanuel. Thank you, you're welcome. So, okay, Walford, thank you very much. You're welcome. So I will just use 2 to 3 minutes to just give a brief history about NAIJA-JUG user group before we welcome our guest speaker tonight. All right, so it's a pleasure to welcome you all to another exciting lightning section after the monthly section we had last week. So this weekly activity called Lightning Talks is organized by NAIJA-JUG user group, and we are really glad to have you join us here tonight. I want to say a very big thank you to JetBrains for their support, and also to the admins for organizing these events. We have Samuel Benga and we have Rosemary currently on the call. Thank you so much for this section. And what do we do at NAIJA-JUG user group? So our main mission is just to learn and then collaborate with other developers. When I say other developers, like Java-related developers, and we come to learn. So it's just basically for learning, growth, and networking. Yeah. So we have monthly section, and we also have lightning section every week. So the main aim of all of these events, we also have boot camp, but we'll be winding that up soon. The main aim of all of these events is just to build a strong space where developers at every stage, beginner level, mid levels, or senior level, has to connect and then upskill and grow together. So we are happy to have you join us. Those are just joining us for the first time. And I promise you that this section is going to be very impactful. Yeah, tonight we have Mr. Victor that will be guiding us through the section tonight. Victor has been preparing for over a month now, so I'm very sure that the fire is very high. So he'll be telling us or walking us through the Java memory model, and I'm very sure Victor is set and ready to have that delivered in the smallest form that we can. I would like putting that we can learn, or will I say we can upscale, yeah, for those that are having issues in that area. So like I always say, I encourage you to unlearn, relearn, and learn. So as a culture in NAIJA-JUG user group, we don't just allow our guest speakers to have the floor without celebrating them. So I would like us to celebrate Mr. Victor before he has the floor with your favorite emoji. So for me, my favorite emoji is love. I'll be sending out love to him. So you can react with your, some persons are not reacting. Is Victor still here?
Yeah, man.
All right, so Mr. Victor, you can have the floor. Thank you.
Thank you. That's Gloria, right?
Yes.
Okay.
Thanks,
Thank you.
Gloria.
So apologies, it's my camera. I tried to turn it on, and for some reason on this device it's not coming up. I had to exit and join multiple times. Okay,
That's
so yeah. All right. Thank you once again, NAIJA-JUG, user group community for this opportunity. Yeah, it really means a lot, and yeah, thank you for reaching out, and let's have a wonderful presentation. All right, so let me see if I can let me share my screen now. Please give me a second. All right, sorry, I had to change my browser, so it wasn't allowing me to share. So let's see where we are now. Kindly confirm that you can see the screen. Oh,
yeah, I can see your screen.
you guys got to see the conclusion. All right, that's fine. Once again, welcome everyone to today's lightning talk. I hope I'm not echoing. You can somebody confirm because I'm using multiple devices at this point.
Your sound is good.
Okay, thank you. So the Java memory model. Now, so I would like to come from the angle of concurrency because basically the Java memory model basically gives us a better understanding of the Java concurrency, right? So I'm sure a couple of us, right, would have written concurrent program, right? And personally, I haven't read several books. For example, JCIP, Java concurrency in practice. When I was reading the book at first, there were a lot of this is not guaranteed, this is not guaranteed, and well, at that point, well, that was the implementation part of concurrency, right? So this is not guaranteed, this is not guaranteed. You cannot guarantee this is going to happen, and that. So, well, it is. I understand the need to abstract the low-level details, right, about why this is like this, and that is why we are having this particular presentation to look a little bit into the low-level uh, implementation, right? So the Java memory model, why exactly is concurrent program in Java? Why do they behave as they do? So that is the aim of this presentation, at least to shed more light into the correctness of our program, concurrent programs, and the rule that make Java concurrent programs correct. So that's basically what we are going to be talking about today. And hopefully, we are also going to have a better understanding, or at least even become more comfortable when we write our visual concurrent code, because that actually matters a lot for me personally, right? Not just absorbing or putting in, because this is the semantic, this is what you're supposed to do and all that. So, all right, so this is what we'll cover. Talk about why memory model, talk about instruction reordering, core concepts, what could go wrong, right? Then, yeah, I'm sure once again, if you've done some level of concurrent programming in Java, know about volatile and synchronized. Then the final safe publication. Then we'll look at some best practices, right, when you're writing concurrent code, concurrent programs. Then summary, and if you want to read further on the topic. So first thing is, why do we need a memory model, right? So if you are looking at how a Java program, for example, compiles, right from the code, then the JavaScript, right, it's compiled, and the class loader picks it up, then the JVM also does some optimization, becomes a machine instruction and all that. Now, there are a lot of independent behaviors, right? In fact, let's even go to a more independent perspective, right? You have different processors, right? We have the ARM, the AMD, right? And each of them also have what we call a memory model, right? It talks about how states are stored, how they are visible to different threads, right? So there's a need to have a Java memory model because we want to be independent of the platform, right? We don't want to tie our implementation to ARM, AMD, isn't it? So the JVM abstract away all of this by having its own memory model. But it is important to know that most architectures also maintain their own memory model, right? So I'll try not to sound too low level, right? So let's look at this from a thread perspective, right? So we have a thread. So you can say thread is basically the smallest unit of execution. So let's say we have two threads now. Now, if you're talking about thread, you're also talking about stack, right? And yeah, a stack would also have its own local cache where it stores a copy of bits, references for objects, or its own what's it called? Its own values, right? Its own values, initializations, right? So now, when we have multiple threads, it is easier for a thread to basically pick up a reference from its own local cache compared to going down to the main memory, that's the heap, right? Of course, the heap in this case is shared. Now, if you have a thread picking up a particular reference from the heap, right, does some computation, right? I'm talking about this thread A, for example. Now, at that point, it is not guaranteed that thread B would see would have visibility into the current changes that thread A has done, isn't it? So now, whenever thread A does some computation, it is required to also update the main memory as well, right? So that other threads accessing that that value, right, or the reference would have the latest value, and they can also have some level of correctness to the computation. Now, this is where it gets interesting. So let's talk about a single thread now, program order in a single thread. Now, if you look at this code by the right, we have the original program, right? So let's say in our usual Java semantics, right? We have integer a equals to 5, b equals to 10, c equals to a plus b. I mean, this is quite simple, right? I mean, looking at it serially, we can, like, just looking at the code, we have a mental picture of the flow. We have a mental journey of how the code part follows, right? But then it's not always true, right? When it comes to the actual compilation and processing of this particular, the original program that you just showed. So the Java memory model allows the compiler and processor to reorder instructions only if the reordered program produces the same result as the original program, right, when executed in a single thread. So basically, there's this as if serial semantics. So it means that, so if you look at this possible optimization now, yeah, integer b is assigned to the value of 10, right? But if you look at the first one, it was done in the opposite direction, right? So a is assigned first, then b, then 10. But then these two programs, the original program and the possible optimized execution, they give us the same result, right? Like they're basically the same semantics. So it is allowed. JVM or the processor can decide to order this execution based on whatever optimization it wants to. Probably maybe this B is already in memory and can easily just set it easily instead of going to fetch it from the memory. Like for whatever reason, I mean, there are a lot of optimization techniques that happens. Then that is not really the scope of this discussion. Now, in a single threaded environment, this is fine. I mean, there's no question of correctness because this is correct. But then this final one, when reordering is not allowed. So if you have integer a equals to 5 and b equals to a plus 1, so you can see that integer b depends on a. So it will not really make sense to want to execute integer b equals to a plus 1 when you are supposed to assign a value to integer a, right? So that's a situation in single thread environment where reordering is not allowed. Not even in single thread environment, even multiple thread, right? As long as there is a dependency between these two lines, then the JVM will not reorder for optimization. Now, but then what if you have a multi-threaded environment now, for example? So this is a simple example to illustrate what would happen. So we have 2 threads, right? And all these values are initialized to 0x is 0, y is 0, a is 0, b is 0. And the 2 threads will run in parallel, right? They're trying to mutate these values. Now, there are different kind of outcome, right? Depending on timing, race condition, data races, and all that can happen. But let's look at the first possible outcome. Now, first, I would like to say that because I'm checking this as correct does not mean that this is a correct execution. It just means that it is something that we can reason, right? So the reason why we can have x equal to 1 and y equal to 0 is, let's say, for a particular timing, thread A is thread A reads B. Thread 1 reads B after thread B has written B. So now we have this thread 1. So it's possible that it's going to read the value of B after thread 2 has written A. So if you look at this thread 2, the first line is that we are saying b equals to 1, right? So it's possible that at the point of reading the value of this b, x equals to b in the first thread, it's possible that thread 2 has run or has splitted. So there's a good chance that x would be 1, right? But at the point of this thread 2, y is equals to a. It's possible that at the same time, this a has not been initialized to 1. So we can have y having a value of 0. I mean, it's just having interwoven behaviors. Say this first part has run, or this first part has not run, then this has run, this has not run. So they are like valid scenario, and the JVM allows it. The second one as well is if you reverse the scenario, right? So let's say this thread 2 now reads a, right? So let's say it reads a. At this point of trying to read the value of a, at the point of reading the value of a, we have y set to 1. So basically, it's this line is executed first, or it is reached first. So y becomes a. But at the point of setting the value of x, this value has not been written. And if you are struggling to understand the behavior of this, I mean, that is how concurrent programs are, and that is why we need to have order, isn't it? Because it is very difficult to visualize, and that's very normal if you are confused. It's difficult to visualize. So this is something you can visualize, right? And the second one is that, I mean, the third one is that we have the first line of each program executing concurrently. So we have a set to 1 and b set to 1, right? But this second line has not been set. So what would happen is that we can have 1 and 1, right? So, I mean, this also makes sense. But then there's also a possible situation where even though these two threads are running concurrently, it's possible that at the point of reading the values of x and y, the read is done before the write. So it's also possible that the value of x and y will remain in the initial state and it will not change. So, well, for me, I think this is chaos, right? And we need to have a level of visibility into values before we access. And this is not a good concurrent program, isn't it? And yeah. So and you might want to question the fact, oh, why do we need to reorder? I mean, it's possible that why not just go sequentially, right? Start with a equals to 1, x equals to b, then b equals to 1, y equals to a. I mean, that's like the way the human brain can easily comprehend programs, right? I mean, it makes sense if I want to read the code and it just goes sequentially, isn't it? Or serially. Now, so a good way to look at this, the benefit of this is that, now, like I said before, I said a thread basically has its own storage area, isn't it? Where, so we have the level 1 cache. So basically, that is more of like the register that is in a particular stack, the frame. So a thread can easily read value from the L1 cache because it is local. It is local to that particular thread. Each thread have their own local storage areas. That is not the heap. The heap is the universal one, right? So if you look at this, benchmark, we have 0.5 nanoseconds when trying to read from the L1 cache. Now compare it with the main memory, for example, from the disk. Can you see the huge difference in time? Like this is 0.5 nanoseconds. Even though this nanoseconds, we understand as like a few 20 milliseconds. I mean, when it comes to API response, this is quite good. But with the way our application processes our code runs, this is very expensive, right? So the JVM deciding on optimizing the code in the order that it feels like, or it thinks it's more optimized. For example, instead of going to main memory to pick the latest one, obviously it's going to be it's going to be easier, right, to just go to the main memory and pick the latest one instead of having to deal with concurrent write and all. But then that is very expensive, right? That would lead to a very slow application, and so this is a valid reason for me. I mean, the difference in time is massive, and this is one of the reason why optimization is very essential, and for scaling as well. So now we've talked about a lot of things, right? And yeah, you're probably thinking we've not really gotten to the Java memory model, talking about so many things. What really is a Java memory model? But it's quite essential to talk about the origin of the problem, right? And what we try to achieve. So with the core concept now, I'll divide it into 3 different parts. The feasibility, like I said, we want to make sure that every thread is seeing the expected value, right? We want to have visibility into the way our program works. We don't want magic. Second thing is atomicity, right? Whenever an operation completes as an indivisible step, right? And the second one is ordering. Want to have a mental picture of the right order, right? And at the same time, it's not only about the mental picture. The right order can make our application perform correctly. So now in the Java memory model documentation from the Java language specification, there's the word happens before is extensively used, right? So what it means is that if an action A happens before action B, everything that action A has done, every effect, every side effect, every action it takes, right, must or should or is guaranteed to be visible to B. So this kind of takes us back to the single-threaded environment where we have correctness and we have order. So it gives order, right? It gives us order to the way our program runs. Not just that, it also gives us visibility. So it's guaranteed that every action that happens in A, right, it's visible in B, or it's visible to B. So it is a formal contract underlying volatile, synchronize, and thread, start, join. So this is going to become like a little bit more intuitive as we go ahead. But just know that the Java memory model is a contract that tells us that, okay, this is what should happen before this. So we have a better guidance to the visibility of states, right, across different threads. So yeah, this is similar to what we did before around visibility, but let's just reinforce what we talked about earlier. So without synchronization now, because the code I showed you earlier, where we could have 4 different values, was not synchronized. So this is also not synchronized. So we have this Boolean flag there, which is ready is equal to false, and we have 2 threads. One thread is writing. So let's say at a particular instant in time, right? We have 2 threads accessing this different method, the writer method and the reader method. So now, what would happen is that this thread B might loop forever. Now, why would it loop forever? It would loop forever, let's say, at the point of writing thread A, if this is reordered, basically, if this ready equals to true, the JVM decides to bring it or set it before setting the value to 42. So it can be reordered. So basically, what that will mean is that we could have the ready being set to true before we set the value as 42 in the first place, right? So if value is set to true, so what would happen is that we can just print 0 and not 42, because at that point, this ready has been reordered. So we cannot guarantee that this value is set to 42 before this thread B reads the value. So what would happen is that the ready equal to true has been called before the order we are seeing at the moment. So it is basically reversed. So it may look forever, or what might happen is that it might just print 0, and that is very inconsistent. So yeah, I think I've touched reading stay values and at the same time reordering. Also, like a lot of these things come with race condition as well. Now, how do we make this particular code? How do we make it synchronized, right? We want to ensure that we have order to this chaos that's currently happening, right? So the first thing we want to do, I mean, the easiest approach to solving this is using the volatile keyword, right? So what volatile keyword does is that it guarantees visibility and ordering for a single variable, but not atomicity of compound operation. So we're talking about if this ready now was like a long now a double, right? And you try to increment, that is not atomic. So that means that the volatile might not help you. It would not help you in this case. You need to use something like a more appropriate class for that, like atomic integer, for example. So now, to solve this particular problem, it's a one-line fix. What we could do is just make this Boolean volatile. So basically, we can add volatile, then Boolean ready equals to false. One-line change. Now, what exactly happens when you say, or when you add volatile to this particular line? What would happen is that every write goes straight to main memory. Every read comes straight from main memory. Always current. So that will mean that every read. So if this thread B tries to read the value of ready, it will always get the latest and the current write. And that means that we also have correctness, right? Another thing again is that we also have this happens before guarantee as well. That means that if this ready now, if it becomes volatile, right, and we're setting it to true, that means that every operation that we can see before ready being set to true will not be reordered. So basically, that means that value equals to 4 will always happen before we set ready equals to true. So what was happening before is that without synchronization, this can be exchanged. This ready equals to 2 can come up, value equals to 42 can come down, right? So because of this reordering, that's a good reason to have like chaos in this program, like unexpected behavior. But then if we have volatile now, volatile enforces that in this particular thread, every effect that happens before volatile is being set will still happen before. So this cannot be reordered to come here, right? So we enforce order to this particular program. And that gives us more visibility to the program. And the issue of reordering as well has kind of been solved for that particular code. Now, another tool is using a synchronized block. So if you have also written concurrent program as well, so I've come across synchronized keyword. So the synchronized keyword basically locks a particular, say, method, right? And what happens is that every thread that accesses that particular method would have to acquire a lock. So when it acquires a lock, subsequent threads that eats the same method would not be able to execute a particular portion of code that is supposedly non-thread safe, right? So because the lock has been acquired, you have to wait until the first thread is done and has exited the synchronized block, then it releases the lock, and after releasing the lock, the next thread in line can pick it up and then perform whatever action you want to perform. Then when it is done, it releases the lock. But then the Java memory model gives us more insight to how synchronized block really work, right? Because it felt like a magic. I mean, you just knew that it blocks this, it blocks that, and I mean, it just saves us from the wrong concurrence programs, right? But what it does in reality is that it's at the point of, say, the first thread now, thread A, accessing a method that has synchronize attached to it. So what happens is that as soon as the method is exited, right, every change, every effect, maybe write or whatever, basically a write action that happens within that synchronized block would be flushed to main memory, and it will be visible to other threads. So you can see, as soon as it releases it now, all the actions is 642. So if we go back here now to this original code now, right? If this writer method, if I decide to just add a single line of synchronize there, so that if I have a synchronized voice synchronized writer, what would happen is that our original fear was this ready for true coming or getting reordered, but then that's not going to happen, right? It will ensure that there's also order, just like the way volatile does. To ensure that every line of code in this particular block it follows the particular order, right? So they'll follow this particular order, and at the point of exiting the synchronized block, what would happen is that it flushes the results to the main memory, the new write to the main memory, and it's visible to subsequent thread that accesses the same object or state. So that's what happens here. So it's kind of like similar to the behavior. Of course, it's not the same thing as volatile, but they have a similar semantic to how they behave in terms of flushing the most recent state within the thread to the main memory, because the main memory is a source of truth, right? And yeah, so it's but then you might want to ask me that, oh, if you are flushing to main memory, right, does it not take us back to the original problem of having to retrieve state from main memory that was very expensive? The diagram I showed earlier, right? So that's a very good question, because with synchronized block, we are basically flushing to main memory, right? And that is where other concurrent best practices, concurrent program best practices come in, like making your synchronized block as small as possible, right? And yeah. So the next thing is immutability. So one of the best advice, I mean, the best approach you can take when writing a concurrent program is making all your states immutable, right? So that was the rule that I knew before. Like, I didn't really know what was the guarantee behind making the fields immutable, right? A couple of tutorials, books as well will say it is safer to just have a final method. It saves the headache of having to worry about the state changing and all that, right? So one easy way to look at it is that if a field is final, that means that it can only, I mean, it doesn't change. So the whole fear of having multiple threads, like mutating, working on the same state, happening like, at the same time, would not happen, right? But then the way the Java memory model, right, describe the behavior is that once a constructor finishes, because if you have a final, right, in a class, that means that you have to create a constructor, right? Basically, you need to have a constructor in it. So once a constructor finishes, any thread that obtains a reference to the class sees the fully initialized X and Y for this particular point class, guaranteed by the JVM's final field semantic. So this is the final field semantic. So the field is final now. So at the point of because the constructor will run first, right? Scored first. So we are sure that the final field, there's no thread is able to access this final field before it is completely initialized, right? So that's a way to look at it as well from the perspective of the Java memory model, alongside the final not changing that I gave at first. But then you need to be careful about publication as well, right? You need to make sure that you are not leaking this like this now. That's the reference to the object. You're not leaking it, because if you are leaking it now, a different thread might access it, and before the constructor is fully initialized, they can have access to a stale value. So that's about the final semantic. So let's put everything in more perspective there. We've talked about a lot, the happens before rule. So let's summarize everything it does. I mean, what it gives us. So the first thing is that order, right? We want to have order. Now, the original program, the first single threaded program I gave, the JVM can decide to reorder program, right? As it seems, or as it feels it's more optimized, right? So that does not give us order, right? Doesn't give us order. But with the happened before, we know that, oh, this particular portion of this code would happen before this. So that way we get a somewhat like sequential, although it's not really sequential, but then it gives us order to our program. Another thing is that an unlock on a monitor happens before every later lock on the same monitor, right? So this is talking about the synchronized approach. So if you take a step backward to this synchronized block here, so you can see it has synchronized, then bracket lock. So usually or commonly you have you just have this like THIS in this parenthesis. So basically it's using the object, it's basically picking the lock on that object, right? So now what it's saying is that the monitor lock, the unlock of a monitor happens before every later lock. So a thread that has acquired a lock must unlock it before another thread locks it. I don't know if that comes out well. But basically, there must be an unlock before a lock. So that's the happens before for monitor lock or synchronized blocks. Then we also have the volatile variable. For volatile variable, the happens before is that a write to a volatile field happens before every later read on that field. So, well, the easier way to just put this is that any write that happens on a volatile field is flushed immediately to the main memory, so that every later read, right, have the visibility to the latest state. So that's a way to put this, right? A write to a volatile field happens before every later read of that field. Then these are also order happens before rule. So we have the thread or start happens before any action in the started thread. So what happened? All right. So in a thread, right? While you're inside the thread, whatever computation is happening inside, the start happens before any of them. I think that quite makes sense, right? Because you need to start a thread before the computation happens inside the thread. So we also have all action in a join. I mean, not in a join. I mean, we are talking about now the thread join now. The thread join happened before. It says that all action in the thread happens before another thread successfully returns from join. So it's kind of like the reverse of the thread that starts, right? So all action in the thread happens before another thread successfully return from the join. So usually you call the join when you want to wait for the thread to finish. So there have to be some action happening in that thread, and those activity must happen before, right? So another thing is transitivity. I think we reference this as well, but it says that if A happens before B and B happens before C, then A happens before C. So, I mean, this is quite illustrative, right? So we have it's similar to the case where I said that you cannot reorder. So here now, right? So if you have A equals to 5, then B equals to A plus 1, right? B depends on A, so we cannot reorder this. We cannot say, or JVM or whatever optimization that happen cannot order this last line before the int A equals to 5, right? So that's a guarantee that we have. So it must happen before the line that depends on it. So we have a common mistake to avoid. So this, well, we can see this as visual concurrency tips. So it's not particular to where you are trying to do clip into memory, Java memory model, right? So double locking without volatile. Double locking, it's the double locking problem. I think this is a legacy problem that people used to do a long time ago, where they are doing double locking, right? You can look up on it where basically they try to avoid synchronization and trying to act to be very clever. But yeah, the solution to the problem with double locking is just to make it volatile. Another thing is that I think I also mentioned this as well, assuming I++ is atomic, right? This is not atomic. It doesn't happen once, although it's a single line. But what happens is that it first read the value of I, it modifies it, and then it writes it. So this is not an atomic operation. So if you are going to do this, you would want to use an atomic integer or put that operation in a synchronized block. Then, yeah, linking this during construction. So similar to safe publication as well, you don't want to expose this reference to the constructor, right? And mixing logs inconsistently. So reading a variable without the same log used to write it provides no visibility guarantee. So in a synchronized block, right? Like I think I mentioned this as well. It's very common to just use this. But instead of using this, you can decide to even create a lock, a different lock instead of using the class as a lock. So you can decide to have a different lock. And so what this is saying is that if you have different monitors, right? Even though you have a synchronized block, there's no guarantee to visibility. It only works when you have the same lock, right? Because with the same lock, that is when the JVM can track that a lock has been acquired or released and all that. So, summarize. I mean, I think it's for the first time, think it's a very hectic topic. I mean, a very difficult topic, because you start to look at programs from a different perspective. It's no longer the common sequential view of programs, right? So, key takeaway to just summarize is that visibility is not free, right? So, a simple checking of a variable, right, to act upon is not free. So, without synchronization, writes may never become visible to other threads. It's possible that that write would first occur in the local cache, right? And it has not been propagated to the main memory before the new thread or the other thread accesses the same value for main memory. So that way there can be discrepancies between the states. Synchronize equals to happens before. So also reinforcing what we said about synchronize, that everything that happens after a synchronized block is exited is flushed to main memory. So everything happens before it's flushed to main memory, and other threads can see it. And that's how synchronize is able to achieve a better concurrent semantics. So the next one is violates orders, doesn't lock. Another very important thing. Yes. So synchronize can lock, right? But violate does not lock. So you need to be careful, because if you're having compound operations, even atomic or not, right? Having multiple atomic operations does not make them atomic as a whole, right? So volatile gives us order. It does not give us lock on that particular block, right? So that's another important to know. So if you're using volatile, you need to be careful with how you write your program. Then final enables safe sharing as well, right? So it ensures that if the object is properly constructed, there's no need to guide the particular state, right? Or the final state. So yeah, that's the end of the discussion. If you want to read further, so the Java memory model, it's a very academic topic, because if you check the way it is being treated in the Java language education, there are a lot of like mathematics, and another thing again that I would like to emphasize on is that the behavior, even though you might not be able to replicate them on your local machine, yeah, but it guarantees them because it is based on an abstract machine, not like an abstract machine that although imitates the behavior of a local machine, but then it's quite academic and there are a lot of things that go on. So if you want to read further, you can check this book. And what helped me a lot for this presentation as well is this YouTube talk by Raphael. So if you want that, I can also share that as well. So I think that would mark the end of my presentation.
Wow, thank you so much, Mr. Victor. Thank you. That was an amazing section. Breaking down Java model in a short while. It is not an easy feat. Well done. Just like you said, Java memory model is an academic. It's like a whole course on its own. We can't finish it at once. Thank you for dropping those recommendation and for those that want to read further. Thank you so much. We appreciate you. Please, if you have any questions, you can signify by raising up your hand. I know Mr. Victor is ready to answer all your questions. If you have any questions, just raise up your virtual hands and ask. Okay, so I want to believe that Victor did justice to the Java memory model. Thank you so much, Victor. I'll just hammer a little bit on the takeaways so that if you don't actually remember anything from tonight's lightning section, you remember those key takeaways. So you always have it in mind that when working with memory, visibility is not always free. So without proper synchronization, other threads might not even know about, or they might completely miss your writes. And volatile orders, they do not always, it doesn't lock. So always ensure to use state flags, not compound atomic actions. And finally, also have it at the back of your mind that whenever you're using the final keywords, it enables safe sharing through immutability. So we should just have that. My colleague just dropped the link to all our social media handles. Please do well to follow us on all our social media handles. We usually have these meetings every Tuesday for our lightning sections and once a month for our monthly sections. It's usually very insightful. Thank you so much, everyone, for joining today's lightning section. Thank you. We hope to see you again. And until next time, have a great night, everyone.